students for the barbecue on that side. We didn't turn on the screen for this.
UC Berkeley's strategy.
Okay, so our last formal lecturer for the session is Bob Stern from UT Dallas. He's going to talk about subduction zones.
Well, thank you very much. It's a real pleasure to be here. Most of you heard my talk last week when I explored when plate tectonics began. So I'm under no illusions that I convinced any of you about my opinions, but let's just take a minute and think about what the general discussion of when plate tectonics began means. It means there's a whole, whenever we could take a poll and each of you could raise your hand for whether you think plate tectonics began in the Hadean or in the Archean or the Paleoproterozoic or the Mesoproterozoic or the Neoproterozoic or even the Phanerozoic. And I don't think we would have all of that much agreement, and there would be quite a vigorous discussion if we did that. But regardless of when we think plate tectonics began, there was something that happened before it. And the transition itself is interesting. How do you go from whatever it was before until up to the point of true plate tectonics like we see today? And a whole set of ancillary questions come up. For example, what would be the effects on climate that the beginning of plate tectonics caused? What would be the effects on life of a change in tectonic regime? Do we need plate tectonics in order to have life? Certainly, or is it intelligent life? When we're looking, one of the most exciting fields of research now is the discovery of new planets in around other stars. It's amazing. We're not anywhere close to identifying intelligent life on any of them, and even if we could, I'm not sure we would want to. But as this branch of very exciting research goes forward, it begs a whole bunch of questions. What are these planets? Okay, so that's an interesting philosophical diversion. But let's get back to what we're doing here, which is exploring the continents. What does this discussion about when plate tectonics began, how can it inform our discussions about the continents? Well, subduction is an incredibly important process. It is arguably the most powerful solid Earth process engine that we have. And if plate tectonics began in the Archean or Hadean, then when you look at these continental growth curves, it's very reasonable to say, okay, that is the way the continents have grown with time. The process has continued for 4.5 billion years, and today we have the end result of these distribution of continents. But if plate tectonics began recently, then what we're looking at with those growth curves in quotes, is what's left. Plate tectonics is an incredibly efficient way to destroy continental crust. So this issue is not just exciting beer talk. It really potentially drives a research agenda for the 21st century. I'm not sure how we move in that direction. It's not something any one of us can do by ourselves, but an interdisciplinary group like this, broadly exploring the history of our planet, would provide some really exciting opportunities to advance our understanding. Regardless of whether you think plate tectonics began early or late, it gets back to the question of what about subduction zones? Subduction zones are these places where we generate crust, and those growth curves represent the addition of those little island arcs over time, or are these things that destroy crust? And it really behooves us to let's think about subduction zones. We can study them today. Let's worry about what happened in the past later. And that's what we'll do today. So do a little bit of terminology. Then we'll take a journey to the center of the Earth. It's a popular pastime. And then finally we'll talk, if we have time, about arc trench systems. And I figure you guys will interrupt me whenever you wake up. So Don't be shy. All right, we sometimes conflate these different terms that we use. Let's get the pointer going here. So we talk about convergent margins, which are a very important part of plate tectonics, one of the three types of plate boundaries. And they're equivalent to a destructive plate boundary. If you think about plate tectonics, it's tectonics on a sphere. And a convergent boundary is simply where one plate disappears. There's nothing about how it extends down for thousands of kilometers. It's a plate tectonic idealization. It's two-dimensional, surface only. Subduction zones, on the other hand, are what convergent margins really are. They're three-dimensional zones of mantle downwelling. And we haven't really done them justice because everything we've shown has been two-dimensional. And in that two-dimensional representation of what plumes going up and slabs going down, you can't see the difference that the thing, whatever depth it's upwelling from, it's pretty much just a point. But the thing that's going down is a wall. So it's a three-dimensional zone of mantle downwelling, and that's a critical thing to pay attention to. But I'll assert that these are by far the most massive and the most powerful of all solid Earth systems. That these are the things that we really have to understand and respect. So arc trench systems, on the other hand, of course, are related to convergent margins and subduction zones, but they're basically surficial regions. They're new or magmatically transformed lithosphere in the hanging wall of a subduction zone, in the overlying part of the subduction zone. So they're, volumetrically, they're trivial parts of any subduction zone, but they're important because they're the part that we get to see, the part that we can sample, and the part that tends to persist over geologic time. The subduction zone itself may end up being a big slab of blueite in the upper mantle, but blues are interpreted in many ways. But so arc trench systems, sometimes we call them island arcs, although you have to keep in mind that many of these superficial expressions of subduction zones are neither islands nor arcs. In the Andes, you're much more likely to get sick from altitude sickness than from seasickness when you study it. So there's 55,000 kilometers of convergent plate margins, mostly around the Pacific and the eastern Indian Ocean, but bits of them have escaped through into the Atlantic and in two places. A little bit here in the Mediterranean, convergence here in southwestern Asia. And then related to subduction zones are collision zones. Collision zones are just subduction zones that have gone pathological. They're places where the dynamics of plate convergence are no longer being honored. There's problems with buoyancy, and most importantly, there's very different rheologies in the materials that are involved in what we call collision zones. Okay. Just to reiterate that subduction zones are the most powerful of all solid Earth systems. Sinking a lithosphere causes the plates to move, mid-ocean ridges to spread. I'll continue to assert that until it's demonstrated otherwise. Dominant mode of mantle convection. Plumes, if they exist, are second-order features. These subduction zones maintain chemical equilibrium between the Earth's surface and mantle, responsible for continental crust, which is also responsible for intelligent life, we think. And, of course, other goodies like ore deposits, earthquakes, explosive volcanism come along with that. Subduction zones really make seismic tomography look good because here you have earthquake sources underneath the region you're interested in. You've got a wealth of information that can be obtained. And so much of what we understand about subduction zones comes from Japan because they're justifiably concerned about understanding what's going on. But we're going to have this same opportunity to use tomography to illuminate a powerful subduction zone as Earthscope and Geoprisms sort of converge on the Aleutian-Alaskan system. Very exciting. Cascadia is a very exciting convergent margin. The problem is, with very few deep earthquakes in that subduction zone, we don't really get the kinds of illumination of these regions that the Japanese and hopefully will get in the Aleutians and Alaska.
In that photo, which parts of the active volcanism, both of those peaks?
That's the magmatic front, and that's a rear arc chain. Okay, one of the problems we have is we don't present this system very well. I encourage you to go on YouTube and search for subduction zone video and see what you find. You'll be appalled. And the problem is that the expertise that understands subduction zones and the technical skill to put together good visualizations are separated. It's going to be a problem, a continuing problem in our science, the representation of important science to people in K-12, lower division universities, the general public, Congress, all of these things. We need to do a better job. And right now, the science is moving ahead incredibly, but the visualization, the animation we should be ashamed of ourselves. And anyway, this is my call for joining the crusade for better subduction zone animations. Now, studying subduction zones is completely interdisciplinary. They're such massive systems, it requires the expertise of everybody that has anything to contribute. Petrologists, geochemists, earthquake seismologists, you name it. It really is an example of the blind man and the elephant. We're talking about things that go on, hundreds, if not thousands of kilometers beneath us. The advances we made on the mid-ocean ridges really have involved understanding processes that extend down a few kilometers or a few tens of kilometers. But subduction zone processes will require being able to understand what's going on down 100 to 1,000 kilometers or more. So I encourage you to join the interdisciplinary international collaborations that are needed in order to advance understanding of these processes. And recognition of that was the NSF Margins program, which ended in 2010 and spawned the Geoprisms program. It'll go on to 2020 with any luck. And with Geoprisms, the geodynamic foci have been on rifting and continental breakup and passive margin evolution on the one hand, and then on the other hand, what's called subduction cycles and deformation, which is focused on subduction processes. So if you want to learn more about that, Geoprisms you can Google that. Peter Van Kecken will be leading the Geoprisms office beginning in October. You can talk to him and invite you to get involved. Anyway, arc trench systems, finally, are the things that sample the products and preserve the record of subduction zone activity. So here's a little cross-section only going down to 150 kilometers because from the point of view of those of us that like igneous rocks, everything exciting happens in not much deeper than 100 kilometers. The downgoing slab, the induced convection in the mantle wedge, and the igneous processes that go on and end up producing volcanoes. Now, there's two kinds of convergent plate margins, and these two communities have sort of evolved separately to study them. On the one hand, you have the arcs that are built on continental crust. For example, the Andes is the end member for that, where you have crust up to 50 kilometers thick or more, where the melts that come out of the subduction zone and the mantle wedge have to traverse a region with very significant possibility of interaction between those mantle-derived melts and both mafic lower crust and felsic upper crust before they get up to the top. These have huge advantages because you can fly there and study them. You have to develop collaborations with people to help you, but you don't need a ship in order to study them. In contrast, the arcs that are built on oceanic crust require research vessels for the most part, or you're just going to be looking at the very tips of the largest volcanoes. These are less accessible, but as a result of having thinner crust, there's less interaction between those magmas and the crust that it has to pass through. So you have a chance to get a less modified sample of that process that generated the melts. So right now, the way we organize science in the United States, we have EAR that sort of supports things that are going on land, and OCE that supports things that are going on in the sea. So we have sort of a structure that separates these two communities, and one of the things that Geoprisms is trying to do is, okay, these are common things, let's get them back together. And in fact, the two focus arcs for Geoprisms, the Cascades and the Aleutians in particular goes from being an on-land arc, Andean margin, if you will, to being an intraoceanic arc, one of the exciting things about it. So what happens in the subduction factory is you have oceanic materials that get brought in and processed in this subduction factory shown here. And you generates volcanoes, earthquakes, volatiles come out, continental crust, and there's residues that don't get recycled back to the surface. It's a big distillery, if you will. So with the margin subduction factory experiment, there were three major questions that we were trying to understand. How do important variables, for example, plate convergence rates, sediment thickness, ages of the subducted plate, control arc magma compositions? How are volatiles such as water and CO2 cycled through subduction zones? And then what are the processes and rates by which subduction zones generate new continental crust? So this is a sort of a representation of that subduction factory. Three arrows. Here's your input, and the input includes the pelagic sediments, the oceanic crust, and then underneath here, not shown so much, is serpentinized lithospheric mantle. That contributes. This circulating asthenospheric mantle contributes. And then finally, the crust that magmas generated deeper pass through contribute. So these three arrows are what we're trying to disentangle when we try to interpret how the igneous rocks that form in arcs capture these three different elements. Okay, so let's take a trip down a subduction zone. And this is Journey to the Center of the Earth. So Jules Verne wrote the story in 1864. The Pat Boone, James Mason version was 1959, and the Brandon Fraser version was 2008. And I'll leave it to you to decide which of these three versions best captures the understanding of the time, the imagination of what it might be, and finally the entertainment value. Okay, so to start with, we have to look at the material that's being fed in, and what's being fed in is oceanic lithosphere. So that includes the sediments. They're typically only about 500 meters thick or so. When you get close to a continent, you can have much thicker sediment, but out in the oceanic realm, most sediment packages going in are on the order of half of a kilometer. Not very thick, but in fact, most of the large ion lithophiles, the continent-forming elements that we see in arc magmas, are thought to come from these sediments. Oceanic crust, the typical 6 or 7 kilometers, is there. Pillared basalts, sheeted dikes, gabbros, altered near the top, and maybe amphibolites near the base. And then finally, one of the exciting areas of research that's happening is trying to figure out what is the mantle component put in. And if it was refractory, Hartsburgite, or Lertzlite, you wouldn't think that it would have much of an effect, much input at all. But recent studies we'll go over show that much of this material is serpentinized. And in fact, most of the water that's carried into subduction zones may be carried down in serpentinized upper mantle. So that's sort of a refraction image offshore of the Marianas, and you can see the very thin sediments, reflections off of the upper pillow basalt layers, the moho. So the first thing that happens is we take that oceanic crust and we rehydrate it. Most of that alteration of the mid-ocean ridge crust happens at the spreading ridge that forms it. Very hot, very fractured, sets up circulation of seawater, black smokers, all kinds of vent communities around them. One of our undergraduates, I asked him if he could generate a nice model. This is actually a plastic model of what happens beneath mid-ocean ridge. And here you can see there's the magma body down at the base of the crust, probably 3 kilometers down. The water can't circulate anywhere near that magma because the water comes out at 400. So this circulation has to be even shallower than that to stay away from the 1200 degrees or so. But black smokers, white smokers. So we end up very quickly taking these fresh pillow basalts and within a few thousands to a few hundreds of thousands of years, turning them into green schist with several percent water in them, and perhaps at greater depth, amphibolite. And these are basically locking water into mid-ocean ridge basalts, which those magmas are the driest on the planet, but once they interact with the hydrothermal system, they are quite hydrated. And maybe it takes 100 million years for this oceanic crust to travel to a trench, but sediments will be deposited on it, and the sedimentary composition varies from arc to arc. That's determined mostly by climate, biological productivity, very variable from convergent margin to convergent margin. This is the one in Japan. And here you can see the plate coming in, and you can follow the plate, and then you sort of lose it down here at 10 or 12 kilometers. That's a model for it, a seismic model for what's happening. Now, one of the things that happens as the plate, that lithosphere, moves across and starts to go down, it has to bend. And that bending much of it happens in the brittle regime. And this is sort of a outer trench profile of that bending. So these are for several arc systems, the Marianas, the Bonines just to the north, the central Aleutians. And what you end up is with a very simplified model for bending of an elastic plate. And you can calculate the elastic plate thickness, the T sub E, and it varies from 42 kilometers to 55 kilometers or so. That's the mechanical plate, mechanical lithosphere, as opposed to thermal lithosphere, which is much thicker, of course. But that bending causes faulting, and we'll see some examples of that. And the idea is that faulting sets up outer rise earthquakes. Some of them are below the moho in the outer rise, and that these faults allow water to come in, and that water serpentinizes the upper mantle, setting up probably what very likely is the largest part of the water that's carried into the subduction zone. You can see that in the focal mechanisms for the Aleutians. This is an old version, but here's the Aleutian Trench and the hanging wall with the Aleutian Islands on it, and have all of these compressional focal mechanisms. The outer rise earthquakes have these extensional focal mechanisms. So the plate here at the top, and for some depth, quite interesting to understand how deep into the lithosphere these extensional faults penetrate, because that's going to provide the water in there. So this is the Marianas. So we're looking at 19 degrees to 14, so that's about 600 kilometers along there. There's the Mariana Trench, and you can see all of these faults on the bending plate. These are serpentine mud volcanoes in the forearc. We'll talk a little bit about them in a bit. And here's a fault, shown in the downgoing plate on this multi-channel seismic line. So what happens is you have mantle peridotite that's probably fresh, not affected by the hydrothermal circulation beneath the mid-ocean ridges. that's carried all the way across the ocean for 100 million years. But when it is involved in this bending regime, seawater interacts with fresh peridotite to make serpentinite. And that is probably what's happening underneath these things. Serpentine is much weaker and much less dense than normal peridotite, so it affects the rheology of the plate and might be one of the ways that we can deal with the fact that you really need a lot of energy to bend dry lithosphere, but probably a hell of a lot less energy to bend weak material. 3 varieties of serpentine minerals, lizardite and chrysotile, break down at pretty low temperatures and pressures, but antigerite can be stable to 650 degrees centigrade and more than 130 kilometers deep. So the geophysicists have started going after this problem. It was first suggested for Central America. Here we've got Nicaragua and Costa Rica. And here's the line of arc volcanoes. And here's active source refraction line with OBSs lined up. And what you can see here is the velocity. Now you'll recall that the velocity below the Moho at something like 6 or 7 kilometers should be about 8 kilometers per second. But what you can see here is that the velocities are well below that, 7s and 6s. And Avendonk et al. A few years ago took Christensen's empirical relationship between seismic velocity and serpentinization and said that there's a gradient. This part of the upper mantle is up to 30% serpentinized, whereas the part that's going underneath Costa Rica is much less serpentinized. So that seems to be at least partly consistent with what we think is happening based on these sort of first-order understandings. Now, one of the things that exciting opportunities for the 21st century is that any kind of system that's pumping in enough water to serpentinize that much upper mantle has to have a surficial expression of vent activity. So there's potentially a whole class of hydrothermal vents on the seafloor that we haven't discovered that are associated with these. And the problem with these kinds of vents is they're low temperature. They're not driven by magma. They're driven by serpentinization reaction and maybe a little bit of heat that's left in the plate. So they're going to be at 60, 70 degrees centigrade maybe. They're not going to put out much particulate matter. They're in very deep water. They're going to be very difficult to find. But if this model is at all correct, there's a whole class of many, many hydrothermal vents on the seafloor at outer rises with associated communities that we need to find, document, and understand. Okay, so eventually the plate actually starts to go down, even though it's really pre-prepared in these, at the ridge and with sediment addition and then at the outer rise. So what happens right when the two plates meet? So a bunch of things can happen. So if there's thick sediment on the downgoing plate, some of it will get scraped off, and you'll build an accretionary wedge. And I think last weekend a lot of you saw that out when you looked at the Franciscan. This is a lot of stuff that was shed off of North America, dumped into the old trench, and got scraped off and came back up. Another thing that can happen if the sediment isn't so thick that it gets scraped off is it can get subducted partway and then what they call underplated. Different kind of underplated than what we talk about magmatically, but the group that's looking at the quartz content of the lower crust is sort of looking at the results of this process, this replating of the lower crust that comes from studies of the Rand schist and the Orocopia schist in Southern California. And then finally, what can happen is subduction can actually calve off pieces of the hanging wall. And this is known as subduction erosion. This is pieces of the hanging wall will be taken, normal faulted in here and taken down. And Dave Scholl and others have, Roland von Huene, have made eloquent arguments that in places where the sediments are very thin, that subduction erosion can cut back the forearc of a convergent margin by up to a kilometer per million years. So this is one of the ways that we lose continental crust. Now in margins, this shallow region where these processes are going on was the realm of the seismogenic zone experiment. And in the Geoprisms, we've folded in seismogenic zone shallow earthquake processes with the subduction factory into this subduction cycles and deformation. So we're talking more closely than we did in margins. But I mean, this is in the news. These things are earth-shaking literal events. The Sendai earthquake, the 2011 earthquake offshore Japan, this was massive slip on a very shallow part of the subduction zone, what we call the seismogenic zone, which extends from about 20 kilometers below sea level to maybe 50. But these are the places where the two plates will lock until strain builds up and suddenly there's a rupture. And the magnitude of the rupture up until Sendai was not really understood. So this is the earthquake cycle that we get for the shallow part of a subduction zone between two plates. So what happens is we have these four steps, the earthquake cycle in the seismogenic zone. So plate convergence is continuous, but the two plates in some places lock up. And they lock up across that plate interface. This causes the upper plate to flex upward. And this uplift of the upper plate, corresponding with down warping closer to the trench, is characteristic of that stage of the seismogenic cycle. And ultimately, strain builds up until it exceeds the strength of the fault. The lock zone breaks, and you get a great earthquake like Sendai. And during the rupture, the built-up strain is released, the uplift subsides, and the hanging wall moves towards the trench. And then the cycle starts over again.
Sorry.
Yes?
In the subduction zone, you should have at least 3 kilometers of serpentinizing material, right?
In the you mean at the interface?
Yeah.
No, I don't think so.
Yeah, that's why they're locked.
Serpentinite, what we've learned from Parkview is that serpentin talc in particular makes faults weak, and that's why that segment of San Andreas is creeping. The serpentine comes down here, and it may be responsible for region, maybe the lower depth limit of the seismogenic zone. But no, if there was serpentine in here, Sendai wouldn't have happened, I don't think. So you've got to get below the crust, and it's going to be the hanging wall crust that has the serpentine. Oops. Okay. So the Japanese have studied this in great detail. This is the region of slip modeled from the motion, ground motion, with the greatest slip actually out at the near the trench. From the teleseismic, slightly different slip areas shown, but still these are huge areas. That's 4 degrees. That's 4 degrees. And then from the tsunami modeling, that slip was largest out of the trench. And the problem, with GPS, we have a wonderful way for telling you what the land's doing. And this is the GPS from the Japanese network. And you can see that motion towards the trench was increasing towards the coastline and was certainly higher offshore. And just as important is this vertical motion, which shows subsidence all through here, as we'd expect from that simple cartoon of the seismogenic zone. But we don't really know what happened at the trench. So the Japanese went out and fortunately, they'd surveyed this region with swath bathymetry before, and they came back and did it again. Let's see. So that's before and after. this is the thing. From the comparison of swath bathymetry, they determined that there was 50 meters of motion, horizontal motion at the trench. I mean, 50 meters it's unimaginable before this earthquake that the Earth could move that much in a single event. It's still a stunning indication of the power of these systems and why we need to understand them better. Okay, so the 13 biggest earthquakes that we've ever had, all of them are on these part of the subduction zone. So some of them were surprises, like Indonesia in 2004, but all of these are instrumented except for the Cascadia, the 1700 Cascadia, which is thought to have been a 9.0. It's shown on there simply because people in Oregon and Washington and Northern California don't really grasp the severity of the situation. But fortunately, the biggest ones are in almost unpopulated parts of Alaska, which for the Geoprisms initiative is very exciting because the amount of energy that's going to be illuminating the subduction zone is going to be remarkable. And then, of course, down here in Chile. Okay, so those giant earthquakes that cause so much damage and tsunamis, these are all in the shallowest part of subduction zones, 20 to 50 kilometers deep. Now, subduction zones are characterized by earthquakes extending down to actually 670 kilometers. This is a really remarkable thing because in most of the Earth, we get earthquakes down to 20 kilometers or so, maybe 30. Here, it goes down to almost 20 times greater depth. And earthquakes are, into a first order, pretty simple to understand. Earthquakes mark where the Earth is brittle, which means cold, and can break, because we know that hot things flow, but cold things break. So here we have a region of the Earth that's so much colder than any adjacent region because of what's happening in a subduction zone. Now, key to our understanding of what's going on in the subduction zone has been the work of Wada and Wang and others. And basically what they did is said, okay, what happens in the shallowest part of the subduction zone is that you have, and it gets confusing because this is called the decoupled zone. And in fact, I just described what happens in the earthquake cycle as a result of coupling. But over the long term, this is decoupled. You know, for a few years or a few centuries, it might well stay coupled, but ultimately there will be a slip, and that is what's being shown here. This is the decoupled zone. Below that, there is full coupling between the downgoing slab and the mantle, and that makes all the difference for controlling the thermal structure of a subduction zone, because where you have coupling between the downgoing plate and at deep enough depth, the asthenospheric mantle, you get flow. That asthenospheric mantle is dragged along with the downgoing plate, and you get constant replenishment of asthenosphere into this part of what we call the mantle wedge. Shallower than this, that mantle is not brought into convection. It is just sitting there, and as we'll see, most of the fluids that come off subduction zones come off very shallow. So this mantle is just sitting here, receiving most of the water coming up. It serpentinizes, and especially the mantle above the zone of basically this maximum depth of decoupling is serpentinized. This mantle is not. This mantle is asthenospheric mantle brought in. Yes, it has to be below where above where the region of the stenospheric inflow. So about there. So you can argue exactly where, but one of the things we see at the surface is what's called the volcanic front. I prefer the magmatic front because it's not just volcanism, it's also intrusion of igneous rocks. But that is typically a couple hundred kilometers from the trench. And this region in here, as we'll see, is cold. So one of the things we need is more heat flow measurements over convergent margins. But in this region, this is Japan. Here you can see the data points. And the heat flow is on the order of 20 or 30 milliwatts per meter square in the forearc, very characteristic of forearcs to be very cold. And then around the arc, it jumps up to very high values. And one of the things that many people have noticed is that as you go from that volcanic front towards the rear arc, the heat flow is higher, the volcanism is more broadly distributed. It's a completely different mantle region here than here. So these are Van Kekken's et al.'s models for how you can cause that, basically looking at the shear heating on the slab overhanging wall surface. It doesn't cause very much except way out in the trench. But this magmatic front overlies the region that separates the region of coupling from the region of decoupling. Right? You sort of put that heat flow map here, we would see it look like that. Okay, so this cold region in the forearc, here's we're looking at the Marianas, is in a thermal condition that favors serpentinization. So this is the Marianas, and this is the modeling result, Wada and Wang across that margin, the available heat flow, and this region is very cold, and so the fluids coming off the slab serpentinize that. And in the Marianas, we see direct evidence of that forearc mantle being serpentinized because we have serpentine mud volcanoes. These have the form of volcanoes, but these are actual volcanoes with hot magma coming out. These are volcanoes with cold serpentine mud flows coming out. Some of them look like that. I mean, the physics of constructing a pile of serpentine mud flows is not really much different than the process of making a big pile of lava. But the implications for the thermal structure are quite different. And these are associated with vents, fluid vents, and chimneys, quite different than the ones you see in mid-ocean ridges, which are sulfide-dominated. These are carbonate-dominated chimneys. So you don't see these serpentine mud volcanoes in very many arcs. You could argue that there are good examples of them in the coast ranges of California, where you can see serpentine mud flows mixed in with the Cretaceous sediments. And that's probably a really good place to study the phenomenon. So far I've described just a generic subduction zone, the oceanic lithosphere. It doesn't matter whether it's old or young. But in fact, we know that the age of the oceanic lithosphere is a very important control on how a subduction zone behaves. So, what is that? More than 40 years ago, Ueda and Kanamori proposed that there were end members of subduction zones that really reflected, more than anything else, the age of the lithosphere that was being subducted. That when you subducted very young oceanic lithosphere, it's quite buoyant, and it resisted subduction, and you ended up with a shallow dipping subduction zone and great compressional earthquakes. And the other extreme, if you had old oceanic lithosphere, it would be very negatively buoyant and sink rapidly, and you get something like a vertical subduction zone. And you can see the differences between these two convergent margins in the back arc regions. so that you would get back arc compression in something like South America, where you have the fold and thrust belt behind the southern Andes, and you would get back arc extension to the point of seafloor spreading in something like the Marianas or Tonga. So very different responses to the buoyancy of different types of lithosphere. And to a certain extent, what's happening here is like collision. Not really India colliding with Asia, but an oceanic plateau like Ontong, Java represents a buoyancy that causes problems for a subduction zone. It's not only the strain in the upper plate that reflects the difference in the oceanic lithosphere, it's also the thermal structure of the subduction zone. So here we have a couple of the more recent models for thermal structure of a subduction zone. For example, northeast Honshu, where you're subducting early Cretaceous, 100 million year old seafloor, versus southwest Japan, which is subducting 20 million year old oceanic lithosphere. So this is what we call a cold subduction zone, and this is what we call a warm subduction zone. Most of the subduction zones in the eastern Pacific are warm subduction zones. Most of the ones in the western Pacific are cold subduction zones. And what you can see is the temperature at this interface between this downgoing slab and the overlying mantle wedge is quite different. 650 degrees there beneath the volcanic front versus 900 degrees below the volcanic front there. So that's going to have, as we'll see, big differences on the what happens in the downgoing plate. So one of the keys of understanding subduction zones is that this injection of cold sediments and crust and mantle, sometimes we just call this slab. You'll hear people say that's the downgoing slab. Chills the surrounding mantle, especially beneath the forearc. At greater depth, that hot mantle is dragged in with the subducted slab. Now, these models are always two-dimensional, and as the discussion about shear wave anisotropy showed us, is we really have to consider the third dimension, and we don't show it very well in our cartoons. But this downgoing lithosphere below the coupling zone is responsible for induced convection. And that keeps bringing in new mantle that is undepleted and presents it with a flux of water, and sediment melts off the downgoing slab. And one of the things that we've made good advances in is understanding what the flow fields are. This model is a little bit older, so it doesn't really show the coupling-decoupling zone, which would be maybe about there, which would limit the amount of upwelling into this forearc region. But here you can see something like the two-dimensional flow associated with a downgoing slab. That would be the plate interface right there. So we can look at very simple things. So, for example, the length of a seismic zone measured from the trench down to the depth of the deepest seismicity, and we can multiply that by the convergence rate and come up with something called a thermal parameter. So this shows to a first order that the length of that seismic zone varies very simply with the convergence rate times the age of the seafloor. That if you have old seafloor that's coming in fast, you're going to have a long seismic zone. If you have very young oceanic lithosphere coming in slowly, you'll have a very short seismic zone. So it's a very simple way to understand and to characterize subduction zones is with this thermal parameter. So as we get down below the zone of coupling, where the asthenospheric mantle is flowing in, so what is that, 1,350 degrees, sitting on top of very cold slab, it is going to heat up that slab. And the thing that sits right up against that asthenospheric mantle is going to be the sediments. So if we could take a slice across, let's say take a slice across there, what would we see? Be something like this. So now this is sort of in my mind's eye, but maybe 10 kilometers above the subduction interface, you would have hot asthenospheric mantle, convecting asthenospheric mantle. Between those sediments and altered oceanic crust and the serpentinized mantle, you would have peridotite metasomatized by slab-derived liquids, whether it's water or it's sediment melt or whatever. It's going to interact with this peridotite and transform it. At greater depth, you'll get down into the normal sequence of sediments, pillow basalts, sheeted dikes, gabbros, serpentinized mantle. This is going to be very hot, 1,300 degrees or so. At what distance from the subducted slab will normal asthenospheric temperatures be obtained? That's a good question. At the bottom, you'll be dealing with a very cold slab, and especially the serpentinized mantle, which is going to be 6 or 7 kilometers away from the subduction interface, and any conductive heating by the asthenospheric mantle you're going to have something on the order of almost 1,000-degree difference in temperature over 20 kilometers. Right at the slab interface, it'll be halfway between that, and 800 to 1,000 degrees for the sediments. Sediments are going to be subjected to a thermal regime that will either cause melting or very close to melting. So we can generate thermal models for these two kinds of subduction zones. Old cold slab. These models really come from Japan, so this would be northeast Japan. But we can treat it like the Izu, Bonin, Mariana Arc. So the solid lines are the Izu, any old cold subducted slab, and the temperatures at the moho. You can see how cool that is, versus the top of the crust. Here in green is the top of the crust, and the top of the sediment in red. So that part of the downgoing slab is going to be really heated up. That kink corresponds to that where coupling, decoupling happens. And all of these thermal models have to pay attention to, okay, where do you put the coupling, decoupling depth? If you put it down here at something like 70 kilometers, you'll get that kind of a kink. Now, if you take a young hot slab like Central America or Cascadia, or in this case, Southwest Japan, the base of the moho is not nearly as cool because this is young hot oceanic seafloor. So it's maybe 500 degrees hotter than the moho for an old cold slab. But the sediment top and the crust top is not going to be all that different than what happens in an old cold subduction zone. Okay? So those are the ways right now that we look at the thermal structure in the downgoing slab. Hottest right there at the top of the slab, a little bit cooler at the top of the basalts, and a whole lot cooler at the moho. Yeah, but well, I mean, it does speak to your intuition. So the physical properties of two plates at very shallow depths, they're going to rupture over some time scale, and as we see spectacularly at Sendai. And then now, one of the areas of tremendous understanding are these zones of aseismic tremor and slip, where there's these slow earthquakes, and that happens at slightly greater depth. And then so the bottom of the seismic tremor and slip zone is maybe what? Somebody know? 760 kilometers? I don't know, something like that. And most of these models like something closer to 80 kilometers for the coupling-decoupling zone. It's surely a transition, but the way that the two plates behave is going to control that thermal structure. This idea of this coupling-decoupling zone is relatively recent, and it was forced most of all to explain these thermal models, and also the fact that in the four arcs you get serpentinization, but beneath the arcs you've got to have normal asthenosphere. But that's a pretty exciting area of research for people that want to get into it. Yes?
I think the zone of the aseismic tremor slope isn't really well constrained because it's really difficult to locate those tremor amounts.
Yeah.
So there's a big area around that.
Yeah, but they're working on it, and it was one of these remarkable things that fell out of the GPS. That the use of a new technology, and it's like, what is that? And it's really a remarkable thing.
Does the coupling have to be 100%?
Eventually, yeah. I don't think at depths of let's say 4 GPa that there's any slip between them. I don't know that would be true, but it seems that the coupling there would be more and better coupling with more and more pressure. But how does water behave? One of the ideas that Hugh Davies proposed a couple decades ago was the way the water gets out of the system is hydrofracking. I don't think there's any seismological support for that idea, but maybe there's so much water that maintains a zone of weakness across the interface. But these are very simple concepts that explain the first order problem, which is the heat flow. But in detail, we know it's more complicated. And I'm sort of in a position of an interested observer as the physical properties people and the GPS geodynamicists and those people sort it out and tell me what they found. So our understanding is that this subducted slab releases water and associated trace elements. And to a first order, for those of you that aren't geochemists, the sediments now are generally agreed to melt. The oceanic crust is now generally agreed to dehydrate. And the serpentinized mantle wedge sole also contributes, but we really don't know how much how much water is in that serpentinized downgoing slab, and B, how much of whatever water there is taken out. We think because of our understanding of the thermal regime that the sediments are the most affected, and the gabbro, the basalts are also affected, but we're not so sure about what's going on with the serpentinized mantle. So that gets us back to this cartoon. So in our mind's eye, what might this thing look like? This region where you've got tremendous chemical disequilibrium, and the water whatever water is being sweated out of here has to pass up through there. What is that? Do we have any geologic analogies for what those look like? And that's on the order of 500 meters. And Mike Brown gave me this photograph in Antarctica of a 480-meter tall cliff of anatectic sheets of leucogranite in a metasedimentary series. So maybe it looks something like this with regions of foliated sediments and small melt pockets organizing and flowing. It's as good of a geological representation of what might be down there as I can think of. So the sediments have their own story, and they're very exciting because they contribute so much of the large ion lithophile elements, the continent-forming elements. But in a lot of ways, our understanding of thermal structure of subduction zones comes from understanding the subducted oceanic crust. And for that, we need to go to metamorphic petrology. And this is my understanding of metamorphic petrology, that you have rocks that are unmetamorphosed. This one is very fresh, and that if you subject them to heating and dewatering, you will get a metamorphosed equivalent that also has its uses. So, yeah, I've now told you everything I know about metamorphic petrology. Okay, so what happens is you take these altered oceanic basalts. I mean, these pillow basalts, when they come out of the mid-ocean ridge, they have basically zero water. But subjected to this hydrothermal regime, they get intensely watered. So maybe 10% water in some of these ugly things. It's really a lot of chlorite, a lot of epidote, a lot of stuff. As you take it down to a subduction zone, it turns into one of our favorite rocks, blue schist, and that has got a fair amount less of water, 5%. And then at greater depth, you get amphibolite with maybe 3%, but ultimately you end up with eclogite, which is very anhydrous, less than 1% water. So this metamorphism, what we call prograde metamorphism, taking these altered ugly rocks and drying them out in a subduction zone, is what's producing the water. So the thermal structure of any of these subduction zones is going to be controlled when those reactions happen. So here we see a cold subduction zone like Central Honshu, hot subduction zone like Cascadia, and in between a warm one. So 130 million year old seafloor, 27 million year old seafloor, 10 million year old seafloor. And what you can see here is sediments, lavas and dikes, gabbro, and peridotite, that upper few kilometers that's serpentinized, and what the metamorphic rocks would be modeled to be, equilibrium. This is all coming from Perplex and Van Kecken's thermal models. And so this is showing them at true scale, and this is showing them sort of expanded. And I'll just draw your attention to the blue schist, what's going on with the blue schist transformation, because that's a great rock. You know, here in these old cold subduction zones, it's down at 80 to 100 kilometers. Over in Cascadia, it's at, what is that? Probably 40, and very narrow. So all of these reactions have to be adjusted in subduction zones. And with these prograde reactions, we can calculate water fluxes, making some reasonable assumptions about how much water is released during these reactions. So here you can see water content for those same things, and most of the water up here in the top, and most of it variably being lost. Okay, so we can work out the water fluxing out of the subducted slab using our understanding of metamorphic petrology.
But I can ask a question.
Yeah.
On destruction, you assume that the phases are in equilibrium.
Yes. It's perplexed. So the thermal.
On the slab, you can have the possibility of metastability.
Oh, absolutely. I think that there's no doubt that these reactions are going to go more slowly than would be expected from thermodynamics, but we can't model that very well. I mean, we can see in subducted slabs that metastability exists because some of the deep seismicity is thought to reflect sort of late transformation of olivine to the spinel phase at much greater depths than we would have predicted from equilibrium. But yeah, metastability, yeah. Don, you got to...
You made a very strong case that you have effectively complete decoupling below some depth between the slab and the overlying mantle.
Complete coupling.
Complete decoupling below it, deeper than some depth.
Complete coupling. Not decoupling. Decoupling shallow, coupling deep. Over long. So the confusion, I think, comes from the time scales. That you have, in the shallow depths, you have coupling over the first part of the earthquake cycle, but ultimately it decouples. But never decouples below that, say, 70 kilometers, 80 kilometers.
Below 70 kilometers, the downlying slab drags the mantle with
Yes.
it.
Yes.
And that sets up the circulation.
Yes.
Okay.
Yes.
This difference of the age and the temperature the water release
I'm probably the wrong person to ask. not.
Difference like 100 meters from 130 to 10 meters. The difference of age. Look at the difference of the volume. Then you make blue schist. And what?
This would be interesting to do for the Archean. So, but what you would need to do would come up with oceanic crust. The oceanic crust that existed in the Archean would have been different. It would have had more komatiite. It would have been thicker because the mantle potential temperature would be higher. Going through what the, first order principles would lead you to think that a subducted Archean slab would look like would be a useful exercise. I don't think I'm sure there isn't any exploration at the level of what Van Kecken and Syracuse and those people have done with modern slabs, but it would be a useful thing to do. Is it something that is a reasonable approximation of what could have been reality or not? So I can't answer your question, but it would have been somewhat different. But I think that if you think about the Archean subducted slab, it would have been more like a Cascadia than it would have been like an IBM. Are there good questions? You guys are waking up. All right. Yes.
If we expect full coupling below depths of 70 kilometers, how do we explain the 400 kilometers for earthquakes?
So that's metastability is what most people would argue, that this phase transition, and now there are people that know this better than I do in this room, so you guys need to, if I'm misleading people, my understanding is that the olivine is metastable, it gets carried down, and then all of a sudden it will, for some reason, one place will pop into the spinel phase, and that reaction, pop, 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 it's like a string of firecrackers, sets off other metastable regions in the subducted lithosphere. It's not in the crust, it's in the mantle slab. Yes?
That's really only at about 410 kilometers discontinuity, and in the presence of a lot of water in the slab, you're not going to get a huge amount of metastability. So I don't know if that's necessarily the mechanism.
Well, okay, so let's think about a slab going down. You've got maybe 100 kilometers of thermal lithosphere going down. The top 10 kilometers is hydrated. So those fluids are probably not going to be moving deeper into the subducted lithospheric mantle, my understanding. They would move up, so that's going to stay dry. And it's moving, so kinetics at some point could be retarded. So I don't know. Is there new thinking? Yes, Don.
I think Harry Green is the strongest advocate of this metastability argument in the deep focus earthquakes, but he's also a very strong advocate for, therefore, all the water leaves the slab above it.
I think you can have it both ways because the slab is if you think about the slab is mostly dry. The part that we're interested in is only the top, what's that, 10 kilometers? But that does a lot.
Aren't there some arguments about some water retained in pre-existing fissures that were created at the bending of the slab and went down? And then there is some, hydration left that gets released in some of these deep earthquakes, which somehow explains why the slip is actually on horizontal planes, preferably than vertical planes, because we retain the water more easily. I just heard that recently in some talks.
Yeah, so that.
Well, some of these earthquakes are intra-slab earthquakes. Whatever it means, but they do follow roughly this 700-degree isotope for what it's worth. Maybe related to breakdown of serpentine.
Yeah.
As the isotopes keep.
Well, this gets into another hot topic we'll get into. Any other questions before we move on? Great. Okay. So people are always wanting to try and figure out the mass flux, and this is a particularly important one, are we losing our oceans? Now, obviously, this is Brad Hacker's reconstruction, that about a third of the water that's going into a subduction zone is subducted beyond 4 GPa, which most of us would say, okay, that's lost forever, which should bother those of us that call for subduction continuing over Earth history, but for those of us that would argue that subduction is a recent addition to Earth's tectonic palette, no problem. We've been losing ocean, but we're losing about a third as much water as goes in as comes out, but that's not a big problem if it's only been going on for a short time. But these numbers are changing. Everybody that does them comes up with a different one. Brad Hacker's in a better position to do this than anybody else. Terry Plank sort of has the same story, about when you work the numbers, it looks like we're losing ocean at a pretty good clip. Maybe it comes back up. Okay, one of the exciting areas of curiosity is the double seismic zone. So this is, again, Japan, and you've got tomography here, the downgoing slab. It's not a big surprise. You have a lot of earthquakes near the slab interface. Up here, they're actual faulting on there, or maybe some dehydration and embrittlement. And as you go down, it looks like the earthquakes, this upper zone of earthquakes, gets a little bit deeper. We'll talk a little bit more about that. But problematic is this zone of deep earthquakes that is on the order of 30 kilometers deep in the slab. I don't know of anybody that would advocate water getting to 30 kilometers deep in the slab so that this could represent some kind of a dehydration of serpentinite. And to my understanding, this is completely unexplained, this deeper zone of seismicity. Is that a fair statement? Those of you that know earthquakes better than I do?
Well, I think it was Brzezinski that actually did suggest that those deeper ones are related to serpentines.
If there's that much water getting down there that deep, that is amazing.
Yeah.
So the shallower zone is has been recently interpreted pretty convincingly that what we're seeing in this shallower zone, so there's the two zones of earthquakes, that's the deep one we were just talking about. The shallower zone has been related to the prograde metamorphism we just explored. So this is about 6 kilometers thick, about oceanic crust thickness. This zone, upper zone of seismicity, seems to be related to what we think that would exist for the jadeite, lawsonite, blue schist, and then a little bit deeper, the lawsonite, amphibole, eclogite, and then when everything is converted to eclogite, this upper zone goes quiet. So it seems to have something to do with the loss of water, perhaps dehydration, embrittlement. To me, it's really exciting that we can relate metamorphic petrology to subduction zone seismicity. Because we have this incredible resolution from Japan, we're able to do something like that. I hope we can do something like that with the illusions. You had a question?
Yeah. If there is any systematic difference in the focal mechanisms between the two zones of seismicity?
I can't answer that question. There's so many earthquakes there that.
Well, when they were first discovered, they were planning to be unbending, and therefore an extension. I don't know if that's held up. But isn't there a metamorphic reaction that occurs at those kind of depths because it's much colder and much higher?
Yeah. So this is sort of shown as the sort of boundary between lawsonite, eclogite, and blue schist. So blue schist lawsonite's got a fair amount of water in it, but
I'm talking about the deeper zone.
oh no.
You can't think of any reaction at that depth.
Deserpentinization, but I mean, to me, it defies my question. So this is as deep as. Yeah, let's take a look. Okay. Down to 20, sort of showing it down to 20 kilometers. And this is a hot slab, or at least a warm slab, so you could argue that maybe a cold slab like the Marianas, that zone of serpentinization would extend deeper. So Doug Weens, if he was here, would explain that was the motivation for doing the experiment that they did in the Western Pacific. The problem there is that you're in such great water depths that we really need titanium sphere OBSs to actually put these on the seafloor, and that in the present funding climate is very difficult
Well,
to.
this is pervasive serpentinization. You still have cracks that take some water down deeper, so it doesn't really show up
Yeah.
pervasive volume.
Well, this is his percent serpentinization, so this is mostly above 30% in the blue, and yeah. So it's a question of how deep those cracks go.
How deep do you think those cracks go?
Yeah. Yes.
For what it's worth, some of the outer-rise earthquake studies that I've done have show earthquakes down to within like 15 to 20 kilometers beneath the base of the crust.
Yeah. That's
I don't know if it's
that gets you 25 kilometers deep.
all the way down to that depth.
Yeah.
If there were serpentinization.
Well, if there's that much water being carried down in the subducted lithosphere, then those of you that want to keep plate tectonics going on since the Hadean have got a small problem to deal with. Why does San Francisco Bay exist? Should be a desert out there.
Well, if you have about 10 minutes.
Oh. Oh.
Did you lose a clip?
No, I was just put it here on my phone. Oh, there it is. Oh, okay. That's why. I'll just hold it. Sure. Yeah. All right. Okay. Take me 10 minutes to get back where I was. Dim 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 dim. Okay, so one of the real accomplishments of margins was this correspondence between the thermal models that were developed, and the real breakthrough was having a temperature-dependent viscosity for these geodynamic models of the mantle wedge. So this is the slab surface temperatures that came from these models, most recently by Syracuse, using a decoupling depth at 80 kilometers. And a geochemical thermometer, which represented the ratio of water to cerium, developed by Terry Planck. So it's a really interesting thing. If you think about what comes off the slab, what comes off the sediments, they're going to dominate, especially the cerium budget. It's implicit that the water is also reflecting what's going on in the sediments. And at lower temperatures, there's going to be much less cerium because cerium moves with magma, not with fluids. It's a rare earth. And the water will come off whether you dehydrate or melt the sediments. So that water-cerium ratio is a sensitive geothermometer for the sediment. And what they've shown is a remarkable correspondence between the geochemically inferred slab surface temperatures and the geodynamically calculated slab surface temperatures. So these are all Guatemala, Cascadia, Nicaragua, Mexico, a wide range of calculations and measurements that correspond remarkably well. If you had to say what's the one thing that really knocked your socks off about the margins experiment, I would say that.
That's the correlation coefficient, 0.7.
Yeah. So one of the questions that we often have, and it's something we knew from the earliest day of plate tectonics, was that the vertical distance of the arc volcanoes, the volcanoes of the volcanic front above the subducted slab, was on the order of 110 kilometers. Now, it's a wider spread than that, but still it's a remarkably consistent depth. So what is it that controls that? And obviously one element is this coupling-decoupling zone, which controls the thermal structure of this region. But another one that may be just as important is how wide of a region, what's the turning radius of a asthenosphere? So the asthenosphere is being pulled down, so new stuff is coming in, and it has to change direction. It has to go from moving towards the trench to away from the trench and down. And maybe that's about what it takes to turn a asthenosphere around. It's as good of a guess as any. So let me move through this real quickly. So let's do this. I just want to show one thing is that if you think about what's really coming off the slab at depths, you have to think about the second critical point. And the second critical point, which is between fluid and melt, differs with different compositions. Here's sediment, high magnesium andesite, basalt, and peridotite. So quite a range in temperatures, a significant range in pressures. So above a certain depth, you've got fluids and melts. Below a certain depth, you've got supercritical fluid. So this is Junichi Kimura did this, and what you can see, this is the depth at which you get that transition, about 120 kilometers, and then it goes up much shallower in the subducted sediments, and then comes down like that. And so the behavior of all of these elements in supercritical fluids, how supercritical fluids would interact with the peridotite, those are really interesting opportunities for figuring out what's going on. So let me zip through. Melts, water makes it. Anyway, water makes it melt. Enough said. Let me just say one thing. Okay, we're going to hopefully be drilling into the middle crust of an island arc here. So the Japanese have a drill ship that can drill down to those depths, and that's Chikyu, and hopefully that'll be happening in the next few years. I think there'll be a tremendous opportunity to work on samples, to participate, all sorts of activities. Stay tuned to that. This is where the plan is to drill. So that's where the middle crust comes up. And that's half dome at about 1,400 meters in half dome, and that's about, that little thing there is about 1,400 meters. And the last thing I want to say is this tremendous opportunity between EarthScope transportable array, which will be deployed here sometime, and the Geoprisms focus in the Aleutians. And what I'm really excited about is the Alaska Peninsula. This is an example of continental crust in the process of formation. The oldest rocks are about 200 million years old. It is standing above sea level significantly, so it's probably close to continental crustal thickness, but we don't know because there's no measurements of crustal thickness across the peninsula. We don't know what the compositional stratification, if any, might exist. But here we're looking at a snapshot of continental crust in formation, and here we have true tremendous instrumentation efforts between these two, and I hope there's some way that we can take a look at the Alaska Peninsula and see how arc magmas contribute to the formation of continental crust, as using that as an example. And with that, I see you. I'm done. Thank you very much.
So we have time for questions.
Yes.
Just a note while this slide is up. I mean, it's worth noting as well that there is this open question right now about the offshore deployment.
Yes.
About as many people know, there's a pool of OBSs currently deployed offshore Cascadia, pool of 70 instruments that are out for 4 years consecutively. And so there's a question about what might happen to those instruments next, and whether they would also go and be part of this effort in Alaska. And I mention it because there's questions about whether NSF will fund that kind of effort or not. And so now is a good time for the community to speak up if they think that that's valuable.
No, and how we get these two communities to work together and start this discussion. What can we do with these two things? I mean, I don't think anybody planned that Earthscope and Geoprisms would be in the same place at the same time, but they're going to be there. How can we work? And we have a tremendous amount of seismic energies coming out of the subduction zone. Yes.
So I want to go back to this coupling thing.
Sure.
At the beginning, you made a case for that we should be looking in 3D at the subduction zones, and then you talked strongly about the full, essentially full coupling. So how do you explain, the ideas of corner flow, etc.? Do we need to throw these away?
Well, corner flow originally was the idea, okay, you have a slab going down, and it drags the mantle in, and then people that work on arcs said it doesn't work that way because the forearc's cold. There's no, because all of the geodynamic models had the inflow sort of shallowing and then coming up, so you'd expect,
Sorry,
seafloor
I didn't mean corner flow. I meant, the flow going around the subduction zone.
The asthenospheric flow
yes,
in there.
Right.
Is it? Yeah, and so that's a real problem because the shear wave splitting makes us think maybe we don't really know what the flow is doing, and the problem is the 3 dimensions. So, but I think there has to be a coupling depth. How that transition comes from decoupling to coupling is over what depth range does that happen? That's a wide open question, but our models, our understanding of island arc thermal structure makes sense with something like a coupling zone where uncoupling transitions to coupling. They make sense if we have that, and they don't make sense if we don't.
Don?
You didn't discuss trench retreat. You acted as if everything was sort of a fixed reference system at the trench. Doesn't the trench retreat also affect the flow in the mantle wedge?
Absolutely. Trench rollback, the idea that the slab is not just going down the way. So we have the geometry of the slab from the earthquakes. And so you look at that and you go, okay, that means the slab is basically going from this earthquake to that earthquake. But it's not. For most of them, it's got more of a vertical sinking in there. And we know this has to be because the Pacific Ocean, which is surrounded by subduction zones, is getting smaller. It has to be getting smaller because the Atlantic is opening. And Garfunkel and Alvarez pointed this out many years ago, that these slabs have to have a vertical component that's not captured by the seismicity.
Then don't you have to rethink this whole concept of the slab is driving the mantle flow? The mantle can just be flowing in. It doesn't have to be driven by the slab.
No, I think it still has to be driven by the slab, even though the vectors that you put would have a downward motion on them as well as that sort of rollover thing.
I know you said you think it, but do you really need that kind of triangular corner flow anymore?
We've got to have triangular corner flow. If you didn't have new asthenospheric magma coming in, the basalts that would be erupted from any arc would get depleted with time. And in fact, what we see is either there's no change in the composition of the magmas with time, or they get enriched. So you go from early tholeiites to late calcalkaline, ultimately to Shoshonitic.
But vertical sinking and trench retreat will allow you to do that without the slab-driven flow.
Well, I think you can reconcile the two, but this is a question for someone with more geodynamic understanding.
I think we've got to redo and rethink the nature of the flow in the wedge.
So Chris Kincaid, Dave Stegman, and Kelsey Drukin have been doing a lot of work with tank models and numerical modeling about subduction zones. And they've explored pretty much all of these options of trench rollback, trench steepening, flow around the edges of slabs. So they've got some very nice, oh, there's one right there. Some very nice models of this. And I mean, the one thing that's characteristic of all of them is this corner flow. It's actually accelerated when you have trench retreat, because, I mean, in essence, you're creating a bigger vacuum in the wedge and you're just sucking in more mantle. You can also get some neat flow patterns where you have ascending mantle rather than horizontally flowing mantle, which might explain some stuff in the back arc, melting in the back arc. So if you're interested in this, I think this problem's been investigated pretty thoroughly. Just Google Chris Kincaid, and he's got a whole series of papers, probably the last 3 or 4 years, to deal with this.
Any students want to ask some final questions? No? You guys can get the last word. No? Okay. Well, you're free.
Excellent. Thank you.